The ability to describe atoms in terms of their electron configuration provides an extremely useful tool for chemists. We'll see as we go through the rest of this term that the fact that atoms in a same group have the same number of valence electrons goes a long way to explaining why atoms in a given group of the periodic table have very similar properties. There are other so-called periodic properties that we can look at, and we're going to start off in this particular movie looking at a couple of these, right? Periodic properties are properties of atoms that are associated with their place in the periodic table, and trends in those properties can be related to the periodic table. Now, the easiest one of these so-called periodic properties to first of all look at and then explain is so-called atomic size. Now, we can explain atomic size in two ways. First of all, think of an atom like this. There's the nucleus in the middle, and then here is the outermost shell, right? The valence electrons, the electrons that are on the outside of the atom. Well, the atomic radius is defined as the distance between the nucleus, remember the nucleus in the middle, really, really small, the distance between the nucleus and that outermost shell. So you can think of an atom simplistically, but not too erroneously, as being a sphere, nucleus in the middle, and then the valence electrons defining the outer shell of that sphere. Another way to think of the atomic radius is to think of a diatomic species, or at least two atoms of the element next to each other. The distance between the nuclei is equal to 2 of the atomic radii added together. So in other words, half of that internuclear distance is equal to the atomic radius. And a lot of times one can use techniques to determine that internuclear distance and thus determine the atomic radius. There are other ways in which you can determine the atomic radius of a particular atom. We'll talk about those when we get into talking about covalent molecules, which is coming up. Anyway, having defined what the atomic radius is, we can generate two trends associated with the periodic table. First of all, the size of atoms increases as you go down a group because the shell gets bigger. Remember, the radius is defined as being the distance from the nucleus to the outermost shell. The first shell is smaller than the second shell smaller than the third shell, and so on. As you go down a group, the outermost shell is further away. Lithium, the outermost shell, is the 2s, the second shell. Sodium, you've got that valence electron in the 3s, the third shell. Potassium, the valence electron in the fourth shell. Rubidium in the fifth shell, and so on. So one nice easy trend that I want you to remember, because simplistic as it might be, it's extremely important that as you go down a group in the periodic table, the atoms get bigger. Atom size decreases as you go across a period from left to right. The reason for that is that the shell is the same. As you are adding in electrons, they go into the same shell. So as you go across that second row of the periodic table that starts off with lithium and ends up with neon, every electron is going in the second shell, whether it be the 2p or the 2s. The third row from sodium to argon, every electron is going in the third shell, whether it be the 3s or the 3p. So that shell is the same, but the nuclear charge is increasing. In other words, the electrons are feeling more positiveness from the nucleus as you go across the period in the periodic table. So let's just illustrate that. Aluminium, it's neon, 3s2, 3p1. So it's got 3 valence electrons in the third shell, and there are 13 protons sucking the electrons in that third shell into the nucleus. Silicon, you've still got the valence electrons in the third shell, 3s2, 3p2, but now there are 14 protons down there in the nucleus attracting those electrons, sucking them in. 14 protons sucks in more than 13 protons, therefore the third shell is a little bit closer to the nucleus in silicon than in aluminium, so therefore a silicon atom is a little bit smaller than an aluminium atom. And continuing on, phosphorus and sulfur in that same row. Sulfur is smaller than phosphorus because sulfur has 16 protons attracting the electrons in the outermost shell. Phosphorus only has 15 protons attracting the electrons in the outermost shell. Another one is ionization energy. Ionization energy is the energy required to take an atom in the gaseous state, so there's nothing else affecting that atom, and removing an electron for it. You always have to put energy in to remove an electron from an atom, because of course the electron is being attracted to the nucleus. You have to put in enough energy to overcome that attraction. Now, ionization energy decreases down a group, and the reason for that is the shell gets bigger, the electrons are further away from the nucleus, and if the electrons are further away from the nucleus, then they're not going to feel that nuclear attraction nearly to the same extent. We can also say they are more shielded by the other electrons between that outermost electron, that's the one that's going to be removed, and the nucleus, and so the electrons are held less strongly. So if we look at this nice little picture here showing the ionization energy of the groups, here's alkali metals, lithium, higher ionization energy than sodium, higher ionization energy than potassium, than rubidium, and then cesium. We see a more dramatic effect here down the halogens. Fluorine is the top halogen, then chlorine, bromine, iodine. As we go down the halogens, the ionization energy decreases. And I hope that that makes sort of sense to you. The electrons further away from the nucleus, more electrons in between. So therefore, the electron is going to feel less of the nucleus, making it easier to pull away. You have to put less energy in to pull it away. Ionization energy increases across a group from left to right, and if the trend is the opposite for radius, that as the shell gets bigger, the electrons get further away from the nucleus, so therefore the atom's bigger, the ionization energy is smaller. If you remember, for the radius decreases as you go across a group, so it kind of makes sense the ionization energy increases as you go across a group. The shell is the same. The nuclear charge is increasing, again pulling in the shell. So in other words, the electrons are held more strongly. So radius increases down a group, decreases across a period. Ionization energy decreases down a group, increases across a period. Okay, same general phenomenon in the case of both of them, just different effects. Further away, bigger radius, smaller ionization energy. Closer in, smaller radius, larger ionization energy. And one can see a pretty little graph for that, again taken from Chemistry Cube, the book that we use in our first year of the main BSc course. The more alert of you will have noticed on that last slide that while I showed this pretty little picture here, I didn't really dwell on it. And certainly, as we look at this pretty little picture, what I'm showing is, first of all, in blue, the second period, starting at lithium, ending up with neon, and in red, the third period, starting off at sodium, ending up at argon. In both of these periods, the general trend of ionization energy is that as you go from left to right, the ionization energy increases. But there is this cute little zigzag here. Okay, so we go from lithium, no problem, up to beryllium, down to boron, up to nitrogen, down to oxygen. We see the same effect in the third period, sodium up to magnesium, down to aluminium, then up to phosphorus, down ever so slightly, not as significant, but still down to sulfur as we continue on. Okay, there is this zigzag pattern. Emphasizing it, what we expect, for example, in the second period, starting at lithium, going all the way along to neon, we expect them to increase as we go from left to right. So lithium is less than beryllium, beryllium is less than boron, boron less than carbon, etc., all the way up to neon. What we actually see is this zigzag. So lithium indeed is the lowest, but then the next one up is actually boron. We expect it to be beryllium, but it's boron. Boron is actually less than beryllium was. So it goes lithium, then boron, then beryllium. Carbon where we expect, but now the next one after carbon should be nitrogen, but it's not, it's oxygen. So it goes carbon, oxygen, nitrogen, okay, and then fluorine and neon as we would expect. It's the same pattern. if we go into the sodium to argon period. Okay, it goes sodium, and then instead of it being the alkaline earth metal next, it is the icosagen, aluminium, and so it goes sodium, aluminium, magnesium, then silicon, and then instead of phosphorus, the nitrogen being next, it's the chalcogen, sulfur. So aluminium, silicon, sulfur, phosphorus, chlorine, argon. Okay, so this little zigzaggy trend, these zigzag exceptions to the overall trend that ionization energy increases from left to right. Now we can get an understanding of why this might be if we think about the electron configurations. We start off with beryllium. The beryllium electron configuration is helium 2s2. So you've got a filled s subshell at the end of its electron configuration. Everything in beryllium are in filled subshells. When you remove an electron to make the cation, well, then you're obviously removing it from the 2s. So therefore the cation, helium 2s1. So what you had to do in order to ionize beryllium is you not only had to remove an electron, which requires energy, but you also had to break a filled subshell. And filled subshells are nice. Thus, when you have to break a filled subshell, it's going to need a little bit more energy. So beryllium is higher than expected, its ionization energy. It's harder than expected to remove that electron because you're not only removing an electron, you're breaking a filled subshell. Now think of boron. Boron's electron configuration is helium 2s2 2p1. So we got an electron in the p subshell, and when we remove an electron, it will be the one from that p subshell, so we're left with helium 2s2. So in other words, we're going from a situation where you've got an electron in a higher energy subshell, we remove that, and we're left with the only electrons in boron plus being in filled subshells. Thus what you're effectively doing is for boron, you're going from it having an odd electron configuration to where all you've got are filled subshells. That means that yes, you've got to put energy in to remove that p electron, but because when you've removed it, you've got a nicer situation, it means that it's easier than expected. Boron, harder than expected. Sorry, beryllium, harder than expected. Boron, easier than expected. Beryllium, higher than you would expect. Boron, lower than you would expect, to the point that beryllium actually goes above boron. Same idea in the third period. Magnesium, because you've got that filled 3s subshell, breaking it is harder than expected. Aluminium, because you're removing that 3p1 electron to get down to just the 3s2, easier than expected. Okay, so the first flip is because you're messing around with filled 2s and filled 3s subshells, breaking them tougher, making them nicer. Now let's move on to the next one, the whole nitrogen oxygen swap. Nitrogen, helium 2s2 2p3. Now their 2p3 represents a half filled p subshell. That's nice. When we make N+, when we remove the electron, we're having to remove the electron from that nice half-filled p subshell. So it's going to involve breaking that half-filled 2p subshell. That's harder than expected. Half-filled p subshells, nice. Oxygen, well now we've got 2s2 2p4 in the atom. Remove an electron, and now we get down to the 2s2p3. So we go from where we've got a half-filled p subshell plus an electron to now just a half-filled p subshell. We're making that half-filled 2p. That's nicer than one would expect. Thus what we see, nitrogen higher than should be, oxygen lower than should be, to the point that nitrogen gets higher than oxygen. Same effect in the third period. Phosphorus has a half-filled 3p subshell. Sulfur has a half-filled 3p subshell plus an electron. Remove the electron, you get down to the half-filled 3p subshell. Notice that it's harder to break filled subshells than it is half-filled subshells. So thus the effect of breaking the 2s, or making the 2s, breaking the 3s, making the 3s, fairly significant difference whether you're in the second or the third period. However, the difference in the second period is there, difference in the third period, it's there, but not nearly as much. Okay, that half-filled P subshell issue, while significant, not as significant as the filled S subshell. And we can emphasize that by just pointing out that in the second period, neon, of course, has got that 2s2, 2p6. There's a filled P subshell. In order to get down to neon plus, we have to remove an electron from that filled 2p. That's very hard. I want you to bear in mind as we move into the next slide that filled P subshells are really, really, really hard to break. Even harder than half-filled, even harder than filled S subshells. P subshelled, super, 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 super hard to break. Super, 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 super stable. So, just as our last discussion, we're going to go on and talk about successive ionization energies illustrated with the actual values. So it's worth in our first ionization energy here. Here's the values for the first ionization energies highlighted in pink. If you remember, what we see is it generally increases, so 520, 900, 1000, 1500, 1600, 2000. Down into the third period, sort of 500, 600, 800, 1000, 1521. But of course, remember, we have the zigzags there. There's the issues with the 2s, beryllium higher than it should be, boron lower, so flipped, nitrogen associated with the 2p higher than it should be, oxygen lower than it should be. Same issues here with the 3s, magnesium breaking the 3s, higher than aluminium where you make the 3s, and then down here smaller but still there. Okay, phosphorus, you're having to break a half-filled 3p. Sulfur, you are making a half-filled 3p. And notice, of course, that the noble gas is the highest in all of them. So hydrogen to helium, nearly 2400 for helium. Down here, there's neon, higher than anything else, over 2000 down here. Here's argon, higher, 1500. Notice, of course, again, as you go down a group, so helium, 2400, neon, 2100, argon, 1500. Decrease as you go down a group, increase as you go across a period with that zigzag. Now, we're not limited in just removing one electron, so you can talk about a second ionization energy, which is where you take that cation, that positive that has already been formed, and you remove another electron from it to make a 2+. Okay. Now, first thing I want you to notice is that in every single case, the second ionization energy here in blue is bigger than the first ionization energy. That should make sense. You've already removed an electron, so now you've got something positive. It's going to be holding on a little bit more strongly to the remaining electrons, so it's harder to remove a second electron. Okay. Second thing to notice, there is still kind of a little zigzag here. Okay, as we go 1700 to 24, down to 23, up to 28, to 3389, down to 3374. It's a much smaller zigzag, okay, but it's still there. But most importantly, which atom is going to have the highest secondization energy in any period? Well, it's not going to be the noble gas. It's going to be the electron that has the noble gas configuration, okay? And which one has the noble gas configuration when you've removed an electron? It's going to be the alkali metals. So you look here, lithium, 7300, huge jump from the first ionization energy to the second ionization for lithium. If you compare that to the jumps for all the others, it's much, much, much bigger. Because when you lost the electron from lithium, now you have helium. Much, much, much harder to remove a second electron from a noble gas configuration. Here's sodium. Easy to take away the first one, only 500. Much, much, much harder to take away the second one, because sodium, you're now breaking the 2p electron filled subshell. Okay, remember sodium starts off 1s2, 2s2, 2p6, 3s1. Take away the 3s1. Now you're having to take one away from a 2p6. Same for potassium. You're having to try and take an electron away from a 3p6. So alkaline metals have the have the highest second ionization energy, because alkaline metals, once you've taken away one electron, have a noble gas configuration. Everything filled. Third ionization energy, highlighted there in purple. That's obviously now taking a third electron away. So you take the 2+ cation and remove a third electron. Again, all of them going to be higher than the second the second ionization energy. Here you've already lost 2 electrons. The nucleus is holding on to those electrons really tightly. Much harder to remove a third one. And again, which is the highest in each one of these periods? The alkaline earth metals, because once you've removed 2 electrons, alkaline earth metals have filled p subshells from which you're removing the next one. Alkaline earth metals have the same electron configuration. They are isoelectronic to a noble gas. So you can see in the beryllium, higher than any of its little friends here. Magnesium, higher than any of its friends here. Okay, so what we've done in this movie is we looked at 2 periodic properties and we have explained observed trends in terms of electron configurations. Electron configurations are a very powerful tool in which to explain observed properties of atoms. And now we're going to move on from considering just individual atoms to how do atoms get together to make molecules and compounds.